Hidden in our past are secrets from extraterrestrial visitors that crossed the solar system to offer clues about our planet and our universe. The clues suggest these visitors could wipe out our civilization. Maybe they destroyed the dinosaurs, but they could have brought life to Earth. They are meteors, comets, and asteroids. It's not a question of if, but when the next deadly impact will take place. It's morning in Boston. Kids head for school. The mad dash to work begins. Then slows to a crawl. From Faneuil Hall on the waterfront to Newbury Street in the Back Bay, the city greets another day. But thousands of miles out in space, a meteoroid is racing towards the Earth at over 45,000 miles per hour. At 40 meters in diameter, it's the size of a small building, yet too small for astronomers to identify in time before impact. Traveling through space for longer than there's been life on Earth, its interplanetary journey will soon come to a violent end as Earth's gravity captures it. As the rocky mass enters the atmosphere, air resistance slows it down slightly and heats it up, causing it to flare into a fireball, until finally the rock completely blows apart. A shockwave with the force of 3 megatons of TNT will slam into the ground. Hot air blasting out from the impact at over 2,000 miles an hour, collapsing every office building nearby. Homes blown to oblivion. The explosion could be seen and heard more than 200 miles away in New York City. And the heart of Boston would be a wasteland. The devastation overwhelming. Hundreds of buildings destroyed. Tens of thousands killed. The costs incalculable, running into the billions. The city in ruin may take years, even decades, to recover. Of course, this is just the stuff of fantasy. Boston is perfectly safe. Luckily, no 40-meter-wide meteorite has ever demolished a metropolis like Boston, yet.
Estimates of the rates at which these things hit the Earth have gone up and down like hemlines over the years. 1970, people thought maybe once every 2,000 years. I think 100 years is a more accurate picture.
What are these objects that fall from the sky? Stones and ions called meteoroids that orbit the sun. Most are tiny, even microscopic. They formed when our solar system did, 4.5 billion years ago. Our solar system evolved from a rotating disk of gas and dust. Gravity collected these interstellar gases and dust into chunks of rocky material that grew bigger over time, coalescing into the 9 planets. At the center, our sun's gravitational pull holds the planets in orbit. But each planet also has its own gravity. Massive Jupiter's gravity is so strong it pulls nearby objects toward it, even as the distant sun's gravity pulls in the opposite direction. Because of this gravitational tug-of-war, our solar system is missing one planet.
In the large space between Mars and Jupiter, where many people always suppose a planet belonged, the gravitational pull of Jupiter prevented the growth of a large planet, and we settled for thousands and thousands of small ones.
These rocks form an orbiting ring called the asteroid belt. An asteroid is simply an especially large meteoroid, usually between 5 and 500 miles in circumference. But most meteoroids are small, and Jupiter's gravitational pull also influences them.
When they get perturbed into an orbit which is too close to Jupiter, they will be swung by Jupiter's immense gravitational field, either into the inner solar system or out. And when they come in, of course, they become Earth-crossing asteroids if they come across the Earth's orbit.
If they cross the Earth's orbit, they could collide with it. Beyond the asteroid belt, there are other rogue bodies, including stray meteoroids and comets. Comets are dirty snowballs of frozen gas and rock formed in the deepest reaches of the solar system, beyond Neptune, that also orbit the Sun.
As the comet approaches the Sun, the ice vaporizes, releases some of the dust, dirt, which make a big fuzzy head. Some of the finer dust goes into the tail.
Though comets rarely hit Earth, dirt from their tails often enters our atmosphere. Our planet gains tens of thousands of tons from all these fast-moving space bodies each year.
The body enters from the coldness of space at cosmic velocity and immediately begins to slow down because of friction with the atmosphere.
The Earth's atmosphere extends more than 600 miles above the planet and is mostly nitrogen and oxygen gas. If the intruding body is large enough, the size of a grain of sand, it will flare up in a visible phenomenon known as a meteor, or shooting star.
We see it without a telescope. It's just very bright. And so for 2 seconds, a speck of dust can brighten up the sky so that we see it as a meteor.
But some meteoroids are big enough to pass through the atmosphere without burning up completely. When they land, they are called meteorites.
Things that we find on the ground, that's what a meteorite is. It doesn't become a meteorite till it actually lands on the ground.
To recap, in space, meteoroid. Very large meteoroid, asteroid. Glowing in the atmosphere, meteor. Landed on the ground, meteorite. The vast majority of meteorites are small, enter undetected, and land harmlessly. Occasionally, they produce vivid fireballs as they decelerate through the atmosphere. In 1992, parts of North America's eastern seaboard witnessed a spectacular fireball.
On a Friday evening during the football season, a meteorite came up the Appalachian, and it was an immense fireball. It broke into pieces.
A young woman named Michelle Knapp was sitting in her apartment and heard a great crash outside, went to investigate, and found her car bashed in. It proved, of course, to be a meteorite.
Another one was witnessed in 1972 in Jackson Hole, Wyoming. This one in broad daylight.
Came through the atmosphere and went right past the mountains.
Some meteorites are downright freakish. In 1953, a Boston paper reported a construction worker hit on the head by a meteorite. In 1954, a meteorite ripped through a roof, ricocheted, and hit a woman sitting on her couch. In 1971, in Wethersfield, Connecticut, a small meteorite crashed through a roof. 11 years later, another meteorite crashed through a house less than a mile away. But these are examples of small objects. There are, however, stealthy giants that lurk in our solar system. Collisions with the big ones are rare, but when they happen, they cause worldwide catastrophe. Science has been slow to acknowledge this threat. Only 40 years ago, most experts weren't sure asteroids and comets even hit the Earth.
So many people doubted it. Geologists, biologists, anthropologists doubted it, and they didn't know the significance of all of it and how interrelated an impact could be.
As we gain insight into these monsters in our heavens, we alter our perception of our planet's history and its safety. When have we been hit before? What would happen if we were hit now? Our history offers geological and historical clues. A typical dawn on the third planet from the Sun 65 million years ago. The skies are filled with hungry pterodactyls. The mighty Tyrannosaurus looks for his next kill. From the northern shoreline to the rolling mountaintops of what is now Central America, creatures get ready for another day. But thousands of miles out in space, a monster is hurtling toward Earth at over 40,000 miles an hour. An iron asteroid is spinning inevitably to a violent collision with planet Earth. At 6 miles across, it's roughly the size of Mount Everest. Too large to pass without incident, it is captured by Earth's gravity. It begins its brief entry into the atmosphere, but its massive size prevents it from decelerating or breaking apart. The asteroid hit the planet with the force of 100 million megatons of TNT, equivalent to more than 7.5 billion Hiroshima bombs, creating a crater roughly 165 miles across. A ball of fire with a radius of 176 miles incinerated everything inside it. 1,000 miles away, a superheated wind traveling at nearly 480 miles per hour set fire to everything in its path. As far away as 200 miles from the impact, molten rock ejected by the initial explosion buried everything. Species vanished in minutes. Within hours, the heat generated from the collision raised temperatures to scorching levels all over the planet, cooking nearly every land creature. Those that remained struggled to survive, but their ordeal wasn't over yet. The sun's warming rays were quickly extinguished in an environment of dirt and soot which lasted for years. The Earth was a desolate landscape, nearly 70% of its species gone. An ice age enveloped the planet for years. Only the hardiest creatures endured. But did it really happen? This scenario, based on a theory to explain the dinosaurs' extinction, was greeted with skepticism when it was introduced in the 1970s.
Geologists and paleontologists were certainly doubtful that this idea of a giant impact being the cause was valid. It was quite a shift from the things they'd been thinking about, like climate change or disease. Suffice to say, a lot of people initially really didn't like the idea.
It took geology to change people's minds. While working at a dig in Gubbio in Italy in the 1970s, Walter Alvarez was intrigued by a thin, dark level of soil at the KT boundary, the line separating the Cretaceous period from the Tertiary period. He examined the soil with his father, Nobel Prize-winning physicist Luis Alvarez.
The Earth is a book, her story told in pages of rock. And at this particular outcropping of rock in Italy, they found out that up until 65 million years ago, there were a lot of these little fossil animals all over the place. And then, none. They just vanished, like they just said, okay, we're done. In between this tiny little layer of dust. And they looked at that dust, and they found that it had a very high concentration of iridium.
Iridium is a trace element, a metal found in minute quantities within Earth's 25-mile thick crust. How could so much have been deposited in such a thin layer of soil? The answer went beyond the mystery of the fossils trapped below the KT boundary. Iridium was found not just in the KT boundary in Italy, but at the KT boundary everywhere. Clues pointed towards the heaven. Comets and asteroids are rich in iridium.
And it was this iridium layer which seemed to be a ubiquitous feature which led them to propose ultimately that there was a giant impact, an asteroid, as they put it, crashing into Earth and leaving its signature, its telltale iridium.
The explosion would have sent iridium particles into the atmosphere to ultimately settle all over the Earth, right at the point when most living things suddenly disappeared.
They got the idea that this disappearance was probably not over hundreds of thousands of years. It may have been over a century. Then they thought it may have been over a few months. And then they thought it might have been over a few weeks.
Science, unaccustomed to abrupt change, preferred uniformitarianism, the idea that the Earth evolved slowly and with small changes over time. Mountains arose, then eroded away over eons. Life developed slowly and uninterrupted from single-celled organisms. But this new theory embraced an idea called catastrophism, which held that events on Earth are occasionally disrupted by huge worldwide calamities. In other words, catastrophic events like asteroid impacts.
When I'm out observing here on a dark night, I look up at the night sky and I imagine myself talking with the Earth. And I hear the Earth answering, yeah, it's peaceful now. But I could tell you about nights when asteroids and comets came out of that sky that you're enjoying so much, and have done such devastation that I shudder to think of it.
Eons ago, the solar system was a more violent place. Earth impacts were once more common, but many asteroids and comets have since crashed into planets or been flung out of the solar system. Currently, the asteroid belt has only 5% of the material it had 4 billion years ago. When Walter and Luis Alvarez and their colleagues proposed one of them wiped out the dinosaurs, there was only one thing missing.
There was a big impact. It should have made a big crater. So where is the crater?
No one was going to believe a giant impact killed off the dinosaurs if there wasn't a massive crater, a smoking gun, to prove the theory. So the search began. But as scientists began looking for this ancient crater, others began to wonder if there wasn't evidence of smaller, later impacts. Perhaps meteors had come streaming out of more recent skies, represented in myth and legend. Meet Bob Haig, the Meteorite Man. With little more than a shovel, a metal detector, and a good pair of eyes, Haig hunts for meteorites, those shooting stars hardy enough to actually make it to the ground. In a field rife with geologists, astronomers, and rocket scientists, Haig is more like Indiana Jones. He's traveled around the world searching for extraterrestrial souvenirs.
I like to say that they've taken me all over the solar system, and they really have. I've searched from Argentina, Australia, South America, Africa, because this is treasure. There are a lot of different kinds of meteorites, and some are more valuable than others. If you find the right meteorite, you could maybe pay your house off. I've seen people driving new cars from finding meteorites.
Haig makes his living finding and selling meteorites. Over the years, he's developed a keen eye for them in the field, and it's a skill he's willing to teach.
If you want to find meteorites, you have to first learn about meteorites. You have to know what they look like. A freshly fallen meteorite will have a melted black burnt skin on the outside of it. It's going so fast, this frozen rock flash fries to this black melted skin. Then there's iron meteorites. So iron's very heavy, it rusts, a magnet will stick to it. It can be picked up with a metal detector. That's the sound you want, guys. You hear that? That's a super high pitch. Hold on. Ah, there it is. Yeah. Here you go. That's an iron meteorite. That's what we're looking for. Woo!
Bob sells his finds to museums, research facilities, and private collectors.
Typical iron meteorites can be worth, $100 a pound or something like that. They can be worth prices like diamonds. You're not going to probably find a diamond in your backyard, but you could find a meteorite. We got one!
A meteorite similar to this one hits the Earth about once every 10 hours. However lucrative his business, Haig is more than a cosmic treasure hunter. First and foremost, he's an enthusiastic collector.
This is another nice one in the collection. This is one we call the Meteorite Man. It has a little character to it, a little bit of pizzazz. It'll up the price and make it a little bit more desirable. So this meteorite has actually traveled all the way around the world from Singapore, South Africa, London, and back to Tucson when I rebought it again. This is a freshly fallen stone meteorite here from Argentina. This one's called La Criolla. It fell in the mayor's yard. They give me a chance to participate in the space program. Really, it's a way to go to the moon and go to Mars and have the stars without leaving the planet.
Collecting meteorites is not a modern phenomenon. Ancient meteorite hunters also found these rocks from the sky valuable, but for different reasons. Iron meteorites were a wonder to earlier civilizations. The metal was very hard, but could be worked into tools and weapons, heralding the Iron Age in human development.
You can imagine in ancient times, because it fell with huge explosions and a fireball and this rock lands at this person's feet, this iron rock. It really was sent from heaven. If you could make a knife out of iron, you had something that nobody had.
Ultimately, meteorites migrated to the center of civil and religious rituals of ancient cultures. Meteorites have been found in tombs and catacombs. A curious rock of unknown origin is enshrined in Mecca. Because of its dark appearance and unusual texture, some have speculated that the black stone of the Kaaba, towards which faithful Muslims face to pray 5 times each day, might be a meteorite. It is said that this once white stone was given to Adam upon his expulsion from paradise, but that it has turned black by absorbing the sins of pilgrims who touch and kiss it. Because the rock is holy, it has never been tested to prove if it is meteoritic. Meteorites may have been worked into weapons and worshipped on altars, but the phenomenon that produces shooting stars was often understood as a sign from the gods. Emperor Constantine may have interpreted a meteor in this way, reshaping history in the process. In 312 AD, Constantine found himself outnumbered on the eve of battle, and he prayed in desperation to the Christian god for guidance, and a vision appeared. Constantine's army claimed they saw a blazing cross in the sky. He won his battle, credited Christianity, and established it as the empire's religion.
He was responsible for changing really the course of Western civilization. And there is a theory that that change came after he saw a fireball, a bright meteor in the sky.
But there might also be a real cause and effect relationship between meteoritic impacts and ancient legends. To find them, we start by looking at ancient texts. Archaeologists tell us that these apocalyptic legends surfaced simultaneously in Bronze Age cultures throughout the Middle and Far East, including ancient Greece. These same cultures also dramatically declined at roughly the same time. Historians refer to this decline as the Greek Dark Ages, though its impact was felt throughout the region. One theory suggests a large meteorite hit the Earth somewhere in the Middle East, creating a fireball and subsequent dust cloud that obscured the sun, causing crops to fail and drought. This would explain the imagery in the legends, but evidence for this cataclysm may exist in, of all places, tree rings.
I'm a dendrochronologist. That's someone who studies tree rings. And we identified a series of what we called narrowest ring events. These were points in time, precisely dated by the tree rings, where a lot of trees all agreed it was the worst conditions they had seen during their lifetime. And the dates which this produced were really quite interesting.
If a meteor impact lifted enough debris into the atmosphere, it would obscure the life-giving sun, causing trees to grow narrower rings. One of the narrow ring events Bailey found could be dated to the decline of the Bronze Age.
So I was intrigued by the fact that our trees showed something like 18 years of narrow rings, implying some sort of really quite severe event. So I became interested in the catastrophic nature of these events.
But Bailey's research also revealed a much more recent anomaly than the Bronze Age event.
The latest of these events was at 540 AD. And what was potentially interesting about that is that it's well into the historic period. So my feeling was, well, here's an event which we should be able to go to the historical record and find out a bit more about.
Bailey looked for references to hellfire in the skies. What he found was a brief but dramatic black hole of information.
It is truly a dark age. There is essentially no good written information just around 540 AD.
The historical record is curiously vague, but when Bailey searched the mythological record, he came face to face with dragons. Legends of dragons, which can also be found in ancient Chinese and Mayan mythology, reappeared in Britain during the 6th century.
It's interesting that the dragon is often described as having a red tail, and a great comet has a red smoky tail. And appearance of these dragons have been associated with a blast on the ground, trees being burned, being pushed over, hot winds, the ground shaking, and so on.
But not everyone agrees with Bailey that he has uncovered evidence of an impact or close comet flyby with his tree ring studies.
We have to be very skeptical about the literal meaning of these traditions, because we have to remember these are not eyewitness accounts.
I'm merely trying to interpret what the trees are saying, and the trees worldwide, remember, are saying that this was a global environmental downturn, and I think we need to get to the bottom of that.
Circumstantial evidence in the historical and mythical records of earlier times may indicate that humans have witnessed, suffered from, and been terrified by impacts from space. But it would take a spectacular meteor fall in a tiny village in France to begin the journey from superstition to science. Geologists and astronomers alike are excited by meteorites, and not just because they are rare, but because they are more than iron and stone.
Meteorites are samples of some of the oldest, most primitive parts of our solar system. And by understanding the starting materials and understanding what we have now as planets, we can put together stories of how worlds are made.
We know what we know about the origins of our solar system, and by extension the universe, based largely on what we found in meteorites. Arizona State University has the largest university-based meteorite collection in the world.
There's two types of meteorites, the stones and the irons. The most common type is the chondrite, the stone meteorite, which typically looks like this on the outside, a kind of a rusty brown looking rock, and on the inside has little tiny flakes of nickel iron metal. A few meteorites, about 3 out of 100, are made entirely of that nickel iron metal.
If you take an iron meteorite and you cut it with a real tough saw, I mean, remember, it's solid steel inside, and then you throw some acid on it, you'll see that a meteorite has a very unique special pattern. It's like its own little fingerprint called a Widmanstätten pattern. And that shows you that they're made of giant crystals because they cooled. It took millions of years for these things to cool. The iron meteorites, you start getting more and more things mixed up inside of them. And sometimes you get a very, very beautiful kind of meteorite. This is called a palisite. And a palisite has these beautiful yellow crystals inside of it. You can see it's a mix of both iron and stone, and the stone is peridot.
Scholars have learned a great deal about our solar system from these extraterrestrial visitors. It is surprising, then, that science questioned their very existence in the not-so-distant past. During the 15th century, people saw the universe through the prisms of two concepts. One, based on the writings of Aristotle, claimed the heavens were perfect, consisting only of the sun, planets, and the earth.
Space was deemed to be empty, absolutely clear of all bodies and phenomena.
The other concept, accepted by the more superstitious, said God could make anything happen. He could even throw rocks from heaven. But it took centuries for science to accept the idea that stones could fall from the heavens. One of the first milestones on the journey from superstition to science came in the year 1492, when a stone meteorite fell in the small village of Ensisheim in the Rhine Valley. On the 7th of November, a sonic boom startled the villagers. A giant fireball, visible up and down the Rhine, sailed across the sky. A 12-year-old boy saw the rock drop into a field. He returned with other people. They discovered a crater with a large rock in the bottom. What makes Ensisheim significant is the fact that this was the first time in recorded history when a stone was witnessed falling from the sky and then recovered. Austrian Archduke and soon-to-be Holy Roman Emperor Maximilian was traveling near Ensisheim en route to fight the French and interpreted the stone as a good omen. He secured its protection from the villagers who had started chipping off souvenirs from this sign from God.
The meteorite was kept in the church. People took care of that meteorite days and nights because this stone was considered to be a sign of God.
Shortly thereafter, Maximilian engaged the French and prevailed. The stone was credited for assisting his victory. The town of Ensisheim still cherishes their treasure. In fact, a group called the Brotherhood of St. George of the Meteorite guards the stone, weighing it annually in a special ritual.
We are very lucky, very proud having a meteorite kept in our museum.
Despite the inescapable reality of this rock, many still interpreted the fall through the prism of superstition or dismissed it as a hoax. Although there were witnesses, scholars still weren't convinced. It would take another 300 years before science accepted what common folk already knew, that rocks do fall from the sky.
Often is the case that academics who know their subject don't accept the word of ordinary people.
Astronomers of the day believed meteorites came from volcanoes or from lightning hitting rocks on the ground. But geologists had by this time chemically analyzed many of these so-called space rocks and found a remarkable similarity. Each one had nickel-iron grains within them. No earth-bound stones contained nickel-iron alloys because conditions don't exist on Earth's surface allowing them to form. In 1794, Ernst Chladni, a German physicist with an interest in astronomy, proposed the heretical notion that meteorites came from space. Experts dismissed him, but Chladni's timing was perfect. He published a book with his theory in 1794 on the eve of 10 years of spectacular meteorite falls, each providing more evidence of Chladni's theory. The crowning proof came in April of 1803 in a French village called L'Aigle, when a cloud approached from the southeast. Then an explosion echoed across the countryside. Suddenly, nearly 3,000 stones rained down onto their town, covering a wide, elliptical area.
The Minister of the Interior assigned the young mineralogist Jean-Baptiste Biot to go and look into the matter. And he did a masterly investigation. He found extremely good evidence of what and where the fall had occurred.
Biot collected so much evidence that he was able to determine the speed and trajectory of the meteor, as well as where it had exploded in the air. The high speed of the meteor alone strongly suggested its origin must have been extraterrestrial. Finally, there was the telltale nickel-iron ratio in the stones he collected.
And he said, "I hope now I have laid to rest one of the most remarkable phenomenon ever imagined by man."
No longer was the solar system perfect and clean and empty of debris. Astronomers had to rethink their understanding of the heavens. These extraterrestrial visitors had destroyed the way generations of scientists had understood their world. But what other theories would these rocky visitors defeat? And what other worlds have they destroyed? The American Museum of Natural History in New York City houses one of the world's largest meteorite collections.
We have over 1,400 specimens of different meteorites. And we make them available to researchers all over the world to determine the compositions of the meteorites.
Visitors can see and even touch small rocks from the distant corners of the solar system. But the museum also houses this monster meteorite. It's the size of a VW Beetle and 40 times as heavy.
It's the largest meteorite in captivity, the largest one in any museum.
The story of how this behemoth called Anikito and two other pieces from the same meteorite found close by ended up here dates back to the Ice Age, somewhere between 10 and 100,000 years ago, in what is now known as Cape York in Greenland.
These were found by the Inuit people centuries ago. They were chipped to get little pieces of iron that could then be embedded in the tips of spears to use as scrapers, harpoon tips.
One of history's most celebrated explorers, Robert Peary, learned of the Inuit source of iron on a visit to Greenland in 1894. No one is sure how the Inuit felt about it, but Peary decided to take the rocks as specimens.
The guide showed him where a couple of these smaller specimens were, but he heard about this bigger piece on an island, and he went and found this piece, but it was so massive at 34 tons that he could not put it on his ship. So they came back again in 1897.
Peary ultimately used 100-ton hydraulic jacks and a steel rail system to lift the meteorite onto his ship. Once it was loaded, they sailed to New York, where Peary hoped to sell the specimens to fund future expeditions to the North Pole.
And this meteorite fragment arrived in the Brooklyn Navy Yard in October of 1897.
The next logistical dilemma was moving it from the Navy Yard to the museum. This created a small uproar in the streets of New York.
You can't have a 28-horse team coming up Broadway without having a lot of attention. And certainly there was a lot of consternation because 34 tons traveling in this tight of a mass puts a tremendous stress on your subway systems, on everything underneath.
These three pieces of the Cape York meteorite are now safely ensconced at the museum, inflicting no serious damage to New York's infrastructure. Apparently, it inflicted no damage when it hit Greenland's ice sheets either. Scientific studies show that there appears to be no impact crater, meaning it must have exploded before hitting the Earth, raining fragments down on the glaciers. Under different circumstances, the Cape York meteorite might have produced a crater like this.
Folks, you're looking at Meteor Crater. 50,000 years ago, a light from the eastern sky grew into a brilliant meteor. This meteorite, weighing several 100,000 tons, 150 feet in diameter, came in at 40,000 miles an hour. And just to give you an idea how fast that is, if you were to get on an airplane in Los Angeles, you would be in New York City in 4 minutes. This crater is now 550 feet deep and almost 2 3/4 miles in circumference. To give you an idea just how big that is, picture, if you will, 20 football games being played simultaneously on the floor of the crater, while 2 million people watch on the sides. If the Washington Monument was standing on the floor right now, we'd be eye level to the very top of it.
Meteor Crater, near Winslow, Arizona, is the best preserved, most studied impact crater on Earth, rich with information on the mechanics of large impacts.
Well, this tremendous classroom. The prime users of this as a classroom were the astronauts. And they went in and out and all around and understood this crater, and then when they went to the moon, they could understand the craters there.
But less than a century ago, no one was even sure a meteorite formed Meteor Crater. Many thought it was of volcanic origin. But Grove Carl Gilbert, head of the US Geological Survey and the most respected geologist of his day, suspected Meteor crater was an impact crater way back in 1891. Locals had found meteoritic iron on the plains around the site. So Gilbert went looking inside the crater for the iron meteorite that created it.
They couldn't find any evidence of a magnetic material in there. So based on this, he concluded that it was not a meteorite impact crater.
Gilbert ultimately assumed lava from a nearby volcanic range had come in contact with an underground aquifer, producing a steam explosion that created the crater.
And once G.K. Gilbert said that, that basically sealed the question for a long time.
That is until Daniel Morrow Barringer learned of the crater. Barringer had made his fortune in mining and was on the lookout for a good investment. Contrary to what the experts said, he knew in his bones that a meteorite had formed the crater, and he was going to find it. Barringer and his family bought the crater in 1902.
They filed a claim on the crater as a place where they might be able to make money mining iron ore.
What he was really looking for was a hunk of iron roughly the size of the crater that would make him even more wealthy. But as Barringer searched in vain for his meteorite, he spent the next decades uncovering evidence for two seemingly incompatible facts. First, that his crater was an impact crater, and second, that there was no meteorite. He found lots of tiny spheres of nickel iron, the signature of a meteorite. In drill holes at the bottom of the crater, he found sludge rich with nickel iron. He kept finding small iron meteorites, but not the giant rock he was looking for.
So for many, many years, he spent the time drilling here and digging here, attempting to find the meteorite and see if they couldn't get something worthwhile from it. In the end, they ran out of money.
Barringer died in 1929 without ever proving his theory. Scientists were skeptical of Barringer's hypothesis. They acknowledged that small meteorites did impact Earth, but they saw no proof that large ones did. No craters covering the Earth, no giant irons on the ground. They assumed large bodies couldn't puncture the Earth's atmosphere. But a mysterious occurrence in Siberia, known as the Tunguska event, would ultimately make scientists re-examine the case for meteorite impacts. On June 30th, 1908, seismographs the world over indicated something powerful made the ground tremble in Russia. But it would take another 19 years before a scientific expedition reached the remote location of the impact. Once there, investigators were startled by the findings.
The nearest eyewitnesses were a family in a tent about 25 miles out from the epicenter. They were thrown out of the tent, knocked unconscious.
1,200 square miles of devastated forest. Trees knocked down in a circle emanating from a swampy epicenter. Evidence of a massive fire, but no meteorite. Scientists determined that whatever struck Siberia hit with the force of more than 20 million tons of TNT, equivalent to 1,500 Hiroshimas. But they also concluded, based on physical evidence and eyewitness accounts, that it blew to pieces in the sky, shattered by atmospheric stress. When bodies traveling at astronomical speeds hit the Earth or its atmosphere, they can be pulverized. Now there was an explanation for where Barringer's meteorite might have gone. The answer was into thin air.
When the meteorite hit, most of it just vaporized or melted, and this was thrown up in the air. It all went up in a great cloud in the air and then fell back down. And then within that debris, we also find little pieces of metal that have been melted, tiny, smaller than BBs, little pieces of metal.
Barringer's meteor turned into iron gas when it hit 50,000 years ago, and the force of this expanding gas carved the crater.
If you stop something instantly that's going 7 miles a second, there's more than enough energy to turn the entire object into gas. If you start with a meteorite that's this big and you turn it into gas, it's suddenly bigger than the whole room, and it just takes everything out of the way with it, and so it blows a hole in the ground.
The proof was in the soil at Meteor Crater. It just needed one person to pull all the evidence together. That man was geologist Gene Shoemaker. In the 1960s, Shoemaker began a quest to learn as much as he could about impact craters. That journey would begin at Meteor Crater.
Let's look now and see what happens during an impact.
Shoemaker would become one of the most celebrated scientists of his era. He had studied nuclear impact craters in Nevada, and he attempted to confirm using physical evidence at the site that Barringer's crater was an impact crater.
One day I persuaded him that he really should stop by and see Meteor Crater, and I think that was a turning point for Gene. He looked at Meteor Crater and he said, "That's just like the craters in Nevada, except it's bigger." And he was able to extrapolate the similarities from one to the other, and it told him a lot about impact cratering.
Synthesizing the work of scientists who preceded him, Shoemaker studied Meteor Crater's rocks under a microscope.
When you smack quartz with an impact very, very hard, it causes the quartz crystals to turn into new minerals. So quartz turns into a mineral called coesite, which turns into a mineral called stishovite.
Shoemaker knew only a meteorite could produce the compression necessary to change quartz into these new minerals. Meteor Crater had to be an impact crater.
Gene Shoemaker started to map the crater geologically, to understand the structure of the crater, to understand what had happened to the rocks when the meteorite hit. He really codified the understanding of the way this crater worked.
Shoemaker confirmed that the theory was correct, and he knew if Meteor Crater was an impact crater, that there must be others. But scientists didn't believe him.
Gene told everyone that the Earth was covered with craters.
If Shoemaker was right, and the world was covered with impact craters, why had no one noticed them before? Where were they? And the biggest question of all, had one of them killed the dinosaurs? Gene Shoemaker confirmed beyond any doubt that Meteor Crater was an impact site. He began searching the world over for the hundreds of other craters he was sure were hiding on our planet's surface, perhaps even larger craters than the one in Arizona. He was convinced the Earth, like the Moon, was covered in impact craters. But most scientists disagreed with the theory, pointing to the absence of large, obvious craters like those on our lunar neighbor. In the 1960s, out to prove the scientific community wrong, Shoemaker journeyed to Nordlingen in Germany, a medieval walled city resting in the immense crater-like Ries Basin.
Many geologists were convinced that it was a volcanic crater. But Gene suspected the Ries Basin as an impact crater, and he suspected it for quite a while.
If this was a meteorite impact crater, it was enormous. Here, from a vantage point on one of the most prominent outcroppings within the 15-mile diameter crater, its rim is barely visible in the distance. There are 99 villages spread across the crater floor. While studying the Reese Basin, Shoemaker hoped to gather evidence to support his theory. The first thing he and a colleague did was sample the rim for coesite and swavite, the transformed shocked quartz that was the signature of an impact. This would tell them for sure if it was or was not an impact site. The next day, he wandered through the streets of Nordlingen. When in front of the city's cathedral, he stopped in his tracks. Before him stood the largest sample of swavite he could have imagined.
Gene walked up to St. George's Cathedral and he said, "This is swavite. It was built out of impact glass." And that was just truly awesome to anyone who studied impact. And I thought, where is Gene's pick? He mustn't knock a block off of the corner of that.
Made from shocked quartz, mined from the crater more than 500 years earlier, the church itself was the proof Shoemaker sought. Nordlingen sits within this ancient impact crater created by a collision roughly 15 million years ago. The crater is so big and so old, hardly anyone had noticed it. Just an hour's drive to the southwest, another smaller crater from the same impact hides in plain sight. It's only 2 miles in diameter, but no one noticed it either. So why weren't these impact craters as well defined as those on the Moon? 2 reasons: the Earth's atmosphere and lava.
The Moon does not know how to erase impacts. They're still there, all the way from the beginning of the solar system. The Earth, though, likes to clean herself up. Erosion takes place, weathering, wind erosion, and rain.
But it's not just erosion. Earth's crust floats on a dynamic molten mantle of rock, shifting whole continents on pieces called plates. Over time, this process called plate tectonics produces mountain ranges and volcanoes. It erases and erodes features like craters. It wasn't until people left the Earth that the extent of impact craters became evident. Aeroplane and satellite images finally proved Gene Shoemaker right. The Earth was covered with impact craters. They found decaying craters on every continent, disguised by geological features and time. By the early 1980s, new imaging techniques, combined with the acceptance of the theory that a giant comet or asteroid impact wiped out the dinosaurs, fueled a global hunt for the big one, the impact crater created by the dinosaur killer. In 1978, geologist Alan Hildebrand learned of a giant 120-mile diameter structure off the Yucatan Peninsula. Geologists studying and charting this portion of the ocean floor for the Mexican oil company Pemex published a paper identifying this large structure near the Mexican village of Chicxulub as a possible impact crater.
You could see an interesting structure on the Yucatan Peninsula, and it certainly looked like it might be a crater, and so this, of course, piqued my interest. I eventually found some samples that had been sent to the University of New Orleans from drilling that was done in the 1970s. And I did a separation, and there were shock quartz grains. And so this, of course, indicated that it was, in fact, a large impact crater.
In addition to the shocked quartz, another key piece of evidence was the KT boundary, the thin layer of soil all over the world that Walter Alvarez had noticed contained high levels of iridium.
The iridium layer turns out to be greatest in the region as you approach the region around Mexico.
There are areas where it is yards and yards thick of breccias and all kinds of broken up rock. Something major happened there, and fast.
Along with the usual telltale signs of impact, such as shocked quartz at the crater, evidence suggests the Chicxulub crater appears to have occurred at the same time as the dinosaur extinction. Hildebrand compared his research with information gathered by others, and much as Gene Shoemaker had done at Meteor crater, concluded that Chicxulub caused the extinction. With the discovery of Chicxulub, the once radical idea that a monster from space wiped out the dinosaurs gained wider acceptance. But not everyone agrees that Chicxulub is the proof. Professor Gerta Keller of Princeton believes Chicxulub is too small to have created so much havoc.
Not all the species went extinct right at that boundary, and there seemed to be a gradual diminishing of diversity through the several million years before the KT boundary and the iridium anomaly.
Keller claims to have found fossils above the KT boundary, suggesting a higher rate of survival. The evidence, surviving as it has on a tumultuous planet for more than 65 million years, remains open to interpretation. But if it is true that asteroids and comets have caused so much devastation on Earth, have they also brought other things less catastrophic? Life, for instance. Antarctica. 5.5 million square miles of ice and snow. Home to only the most hardy, where the average temperature is minus 17 degrees centigrade. In this harsh environment, scientists brave the unforgiving wilderness to hunt for treasure, looking for, of all things, meteorites.
If you go to exactly the right places, you can find hundreds of meteorites. Meteorites are concentrated in certain places in Antarctica by the movements of the ice sheets over hundreds of thousands of years.
The blackened crust that often forms on meteorites as they pass through the Earth's atmosphere also makes them easy to spot on the snowy Antarctic plain. The topography at certain spots prevents the rocks from being covered in ice and snow.
It's as if these meteorites are in a deep freeze. In Antarctica, they can be preserved for up to, as far as we now know, up to at least 2 million years.
William Cassidy first suggested searching here for meteorites in the 1970s, after Japanese scientists found high concentrations of them. Cassidy's plan, the Antarctic Search for Meteorites, or ANSMET, was so successful that researchers have returned almost every year since 1976, collecting hundreds of meteorites. Scientists scour the ice fields on snowmobiles, searching for the next big find, and each one is processed according to a strict protocol.
We then very carefully, with sterilized tools, pack that meteorite away into a bag and then go on to find the next one.
From there, meteorites are sent to the Meteorite Lab at Johnson Space Center in Houston, Texas.
Meteorites are shipped frozen the entire way, and we put them directly in a freezer in our labs. They're eventually moved into a nitrogen cabinet where the samples are dried out under controlled conditions.
Wearing protective gear to prevent biological contamination, technicians sample, classify, and store the meteorites. In 1996, one of these rocks, a large meteorite called ALH 84001, collected more than 10 years earlier in Antarctica, became the most important rock in history.
This meteorite had some glass inclusions in it, and when they picked those glass particles out and degassed them by heating, they got a sample of the Martian atmosphere.
They confirmed the Martian atmosphere within the rock by matching this sample with analysis from the earlier Mars Viking mission, which sampled the planet's atmosphere in the 1970s. This was a rock from Mars. An ancient and massive meteorite impact on Mars had apparently sent material flying back out into space, where it ultimately collided with Earth. But that wasn't why ALH 84001 was so important. This rock would become the center of a media firestorm that would polarize the scientific community.
If this discovery is confirmed, it will surely be one of the most stunning insights into our universe that science has ever uncovered.
The simplest explanation to us is that they are the remains of Martian life.
In 1996, scientists concluded this ancient rock appeared to contain evidence of life.
Not living organisms, but the fossilized and chemical remains of ancient Martian life. And that's why this meteorite has become the center of research over the years.
The evidence included chemicals that formed from the breakdown of bacteria, iron oxide crystals that are formed on Earth by bacteria, and most compelling, what appeared to be fossils.
There are tiny little objects within this meteorite that can only be seen with a high-powered electron microscope that look like fossilized single-celled organisms, fossil bacteria.
The scientists studying the rock determined that with such dramatic news as fossils from another planet, they needed to go public with their results.
After studying it for better than 2 years, the team decided, okay, it's time to lay this hypothesis out to the scientific community. You know, we were overwhelmed with the reaction. It affected everyone from the highest levels of science down to the man or woman on the street, because everyone can relate to, are we alone?
Since that first announcement, some scientists have expressed skepticism about whether ALH 84001 proves the existence of extraterrestrial life.
The original ideas have been now tested for over a decade, and a lot of the original ideas didn't hold up. Some of them may still have a little bit of life left in them, and depending on who you are, that's either enough to make you sure that the theory is right, or basically the proof that says it's not right.
After 8 years, we as a research team still feel that our original lines of evidence stand.
We may not be able to prove that this meteorite does or does not contain evidence of ancient Martian life. The evidence is hard to interpret and is so subtle that we may not know.
But there was another idea, first postulated in the 19th century, that was energized in the dust kicked up by ALH 84001. The idea that life on Earth may have come from space. The theory is called panspermia. One theory of panspermia suggests asteroids and comets may have delivered to Earth the building blocks of life.
Organic molecules form in interstellar clouds, and they form very complex structures, perhaps sugars, amino acids, nucleotide bases. The organic molecules get into comets, and comets hit planets like the Earth and dump these chemical building blocks of life onto a planet,
where perhaps they evolve into life. But there is a more radical version of panspermia that says life already exists in space and thrives there, to be transported intact onto planets.
Once that first living system came into existence, then the incredible survival properties of bacteria takes care of the rest. It would be virtually impossible to destroy microbial life. It would just carry on.
And if life once planted itself here long ago, is that still happening? Could meteorites, even microscopic ones, be assaulting our atmosphere with biologic pathogens, creating diseases, introducing new life forms right now?
You've got to entertain, contemplate the possibility that microorganisms are coming onto the Earth, even at the present time, on a day-to-day basis.
The speed at which radical theories such as panspermia are later proven correct can be startling. In the 1990s, Gene Shoemaker tried to convince the world that it was in danger of an inevitable catastrophic impact.
Yeah, that's it. Oh my God. That's it. Look at that.
But it wasn't until we got a front row seat on just such an impact that anyone listened. By the end of the 20th century, the idea that ancient asteroid and comet collisions had occurred on Earth was gaining wider acceptance, thanks to geologist Alan Hildebrand's theory and the work of geologist Gene Shoemaker. Shoemaker had already proved the Earth had been regularly hit by large bodies in the past and was on a new crusade. He felt the Earth might once again collide with an uncharted object in the near future. To many, his fears seemed less science than science fiction. Experts agreed large collisions had happened in the past, but the odds of something hitting us in the near future seemed minuscule, since collisions appeared to be so rare. Undeterred, Shoemaker, his wife Caroline, and amateur astronomer David Levy began scanning the solar system for large bodies.
In 1993, they were out at the telescope, continuing their survey. They took photographs, and Carolyn Shoemaker was looking at these photographs the next day after they had been developed and discovered the strangest looking object that she had seen.
It appeared as if Caroline Shoemaker had discovered a squashed comet.
I couldn't understand why it would look like someone had stepped on a ball, why it should be so completely weird. I turned to Gene and said, I think you should look at this.
What they discovered was a string of comet fragments, some with a diameter of over a mile, edging dangerously close to Jupiter's powerful and destructive gravitational pull.
And Gene Shoemaker right away thought that it had been catastrophically disrupted. And that turned out to be true. 9 months before discovery, that comet passed within 20,000 kilometers of Jupiter's cloud tops. It's close enough that Jupiter's gravity ripped it apart. Just 2 years later, it would go again to a very close approach with Jupiter. Only this time, it would get so close to Jupiter that it would actually collide with it.
This approaching impact with the pieces of the comet named Shoemaker-Levy 9 gave Shoemaker the opportunity to prove his doubters wrong with what might potentially be the impact of the millennium.
I say today, I have 2 questions. I'll throw them out to anybody on the panel. For the sizes is close.
But even Shoemaker was unsure about how big the impact would be.
There's a fighting chance to get a lot of very exciting science, but I hope everyone will remember there's also a chance that we will see very little. Our range of uncertainty is so wide. Keep your fingers crossed. Let's hope they're as big as Space Telescope observations permit them to be, and then we should have a lot of exciting science to report.
At first, everyone assumed that the gas giant Jupiter might just absorb the impact as the comet began plowing into the planet on the 16th of July, 1994. Then, the giant impact clouds called plumes began to rise.
I'll never forget the look on Gene's face when we're sitting there and he says, You mean they saw plumes?
Look!
Yeah, that's
Oh
it.
my God!
That's it.
Look at that!
Then came the picture from the Hubble Space Telescope. No one had thought that these impacts were going to leave huge, dark, black splotches all over Jupiter's southern hemisphere. From "you ain't gonna see nothing" to "these are the most obvious markings ever seen on Jupiter since Galileo first turned his telescope to Jupiter in 1610. All that change took place within a couple of days. It was just an amazing time.
To Gene and to me, the most significant thing about the impact of SL9 on Jupiter was the fact that it proved that small bodies do hit planets. Gene was probably the most excited person on the planet. When those impacts occurred, it was the culmination of his dreams. Yes, it was wonderful.
Shoemaker produced almost single-handedly a paradigm shift in the way we view the Earth's relationship to space, from one of closed and wholly internal processes to one of catastrophic bombardment. In the wake of Shoemaker-Levy 9, federal and privately funded labs began looking for NEOs, or near-Earth objects, large bodies that might hit the Earth.
The NEAT program, or the Near-Earth Asteroid Tracking, they'll look for things that people haven't found before. Once they're found, they'll try to identify what sort of orbits they are on, whether they're perhaps an asteroid or a comet. We kind of would like to know if anything's headed our way.
Well, LONEOS is the Lowell Observatory Near-Earth Asteroid Search, and our goal is to find asteroids that can come close to the Earth. Our primary tool for the asteroid search is this Schmidt telescope. It's a 24-inch telescope, and its real strength is its wide field capability.
This telescope takes a sequence of photos using a grid of the sky to map areas most likely to produce asteroids and comets.
If we find something that is changing position from image to image, then we become interested in it. And with sufficient positions, the orbit becomes better and better known. And finally, the orbit is known well enough that we can tell whether or not there's any possibility of it ever colliding with Earth.
It took 200 years to find 100,000 asteroids, of which 90,000 actually were found in the last 10 years.
But there is a big task ahead. An estimated 100,000 objects are left to find. Any one of them could catastrophically impact Earth. We are beginning to invest in making our solar system safer, but astronomers have a lot of sky left to search, and that 1 in 20,000 event may be on its way.
If you put all of that into one body or distributed bodies and hit the Earth with that, I think we're talking about the kind of event that's associated with mass extinctions of species on Earth. Now, there's really and truly a global catastrophe. It might not take out the human race, but it would certainly be very bad times.
On the 18th of July, 1997, shortly after the 3rd anniversary of Shoemaker-Levy's impact with Jupiter, Gene Shoemaker was killed in a car accident in Australia.
I think we can make an argument that Gene Shoemaker was the most important planetary scientist in the 20th century. And I think the reason is that he put it all together. It's not that he discovered everything, but that he put it all together. He took the idea that the Earth has had this violent history of impact that framed the development of life on this planet.
Shoemaker made clear the danger we're in. But is there anything we can do about it? Every day, observers armed with telescopes and computers monitor the sky in search of near-Earth objects, NEOs, that could potentially wreak havoc if they come crashing down to Earth.
Here we are living in the 21st century, and we're looking at a period during which the number of asteroids on Earth-crossing orbits has grown exponentially, really, through the result of surveys of the sky.
So we can delete that.
Yep.
Once they spot something scary, the trick is to figure out whether it will find its way to Earth. In other words, calculate its orbit to see where it is going. The laws may be straightforward, but they are not permanent.
Asteroids have chaotic orbits that can only be predicted for perhaps 100-200 years or so.
Gravity, collisions, and a host of other conditions we don't even know about might throw comets and asteroids into and out of our path.
It's not possible to say definitively decades in advance for a newly discovered object where it will hit even, or definitively if it will hit or not. We put a probability on it.
But if the probability is sufficiently high and the date of impact is soon, that requires us to take action.
Unlike earthquakes or tornadoes or hurricanes or other kinds of natural disasters, this may be the only one that we can actually do something about to prevent. We might be able to intercept the object and modify the orbit in order to have it avoid hitting the Earth.
All you need to do is to keep two objects from occupying the same space at the same time. And we know the Earth's going to go around the sun in its regular annual path. And we just want to make sure that when we pass through this area of space, the asteroid comes a little before or a little bit after us.
Experts are developing ways to deflect an NEO. Many think simply blowing up these bodies in space will solve the impact problem. But that would only create a cloud of smaller but still dangerous NEOs. Here, a nuclear warhead might still be useful.
As we send up a spacecraft topped with a nuclear missile, what we want to do is to set off the explosion so that the shock wave would move the thing just a little bit, just nudge it a bit.
You don't need a great deal of impulse to move a small body if you discover it very early. If we can find them far enough in advance, then technology will come to our aid and we'll be able to do something about them.
And there are other ideas. One proposal called CAPS, or Comet Asteroid Protection System, suggests using lasers mounted on roving spacecraft to shift the trajectory of NEOs. These spacecraft would theoretically be patrolling the solar system, possibly engaged in mining missions on asteroids, and would coordinate with observatories based on the moon that continuously scan for NEOs. But are these concepts just science fiction? Can we act in time if we find an incoming body? One mission did prove we could race out to meet an asteroid before it came to meet us. In 1996, NASA launched its ambitious Near-Earth Asteroid Rendezvous, or NEAR, spacecraft, dedicated to studying an asteroid close up. The target was asteroid Eros, an NEO discovered in 1898. Although Eros posed no real threat of hitting the Earth, it was a large and relatively close target. Managed by Johns Hopkins University Applied Physics Laboratory for NASA, this will be the first long-term close look at an asteroid. But the NEAR spacecraft didn't take a direct route on its way to Eros. It also flew close to and photographed another asteroid, 33-mile-wide Matilda, in 1997. NEAR's encounter with Matilda was the closest spacecraft encounter to date, but that record would soon be broken as NEAR headed off to accomplish its principal mission with Eros, an S-class or silicate asteroid in the inner asteroid belt.
The NEAR Shoemaker spacecraft was launched in order to go into orbit around the asteroid Eros. And this allowed us to determine what the asteroid looked like, how much cratering it has, what the surface was like, and also to study its gravity field, which indicated kind of what was beneath the surface.
On the 14th of February 2000, 4 years after its launch and 160 million miles from Earth, the NEAR craft met asteroid Eros face to face. The 21-mile-long, 8-mile-wide body with a 110-meter-high cliff had a potato-shaped appearance. The mission also revealed impact craters. This asteroid had had several run-ins with other asteroids. The NEAR craft was named NEAR Shoemaker, after the late geologist who had devoted so much of his life to studying asteroids and comets. But after all the surface mapping and photographing assignments were over, NEAR Shoemaker had one final mission. It wasn't part of the original plan, but as scientists completed their initial research, mission specialists wondered if they could land on the asteroid.
The mission controllers fired its thrusters, brought it in, fired its thrusters, and slowed it down so that it settled onto the surface.
Photographs recorded the dramatic descent and the highest resolution images ever obtained of an asteroid.
And no one quite believed this would happen. We all desperately hoped it would happen, but no one quite believed that we could do that.
But on the surface, the craft still wasn't dead.
We did, in fact, get some signals back from the spacecraft lying on the surface of the asteroid. It's just amazing.
The NEAR Shoemaker spacecraft still clings to Eros. In a cosmic reversal, the NEAR Shoemaker mission proved we could hit an asteroid, the first step toward being able to move one out of our path.
The NEAR Shoemaker mission was a precursor and showed that techniques that we would use to land on the surface were already mastered.
Each scientific and educational mission moves us closer to solving the bigger problem of a potential NEO collision.
There is still the threat of cosmic disaster hanging over our heads, but since we've become aware of this threat in the last 30 or 40 years, we've made huge advances to assess the problem, to find the asteroids, and to develop technology that will, in the future, help us to mitigate the problem for good.
The next impact, capable of destroying a city, may hit in 10, 100, or even 1,000 years. Whenever it happens, we will probably be prepared for it because of the speed at which our understanding of the universe is increasing. The last 50 years have been a time of rapid and exciting change. Half a century ago, we weren't even sure big impacts occurred. We didn't know our planet was pocked with them. Now we're counting potential monsters and monitoring their movements. Thanks to the work of scientists like Gene Shoemaker and others before and after him, we have embraced science to explain the celestial phenomenon of meteors, comets, and asteroids. After centuries of looking with superstitious eyes to a vaguely menacing sky, now we can at least look with some sense of understanding, if not complete peace.
When I look up in the sky, more than anything, I have a feeling of awe. I tend to think that man is just here for a very short time. We haven't been here very long, and I don't know if we'll be here for very long, but it's probably one of the most exciting periods I could have asked to live in.
As science attempts to make our corner of the sky just a little safer, it has done nothing to diminish the wonders in our skies, especially these strange extraterrestrial visitors, sometimes raining death, maybe even life down on us, but most often simply illuminating the heavens.
Every night on the History Channel from the 23rd of July, beware pirates. Vic Reeves sets out to discover the truth behind some of history's most dangerous seafarers. Find out more at thehistorychannel.co.uk.